Okay, hi class, good morning. Yeah, let's get started. Thank you for joining the poll I sent over the weekend. By a very narrow margin, maybe by 3 votes, people show their preference on spectrum graphic models over machine learning and healthcare applications. So we're going to talk about the graphic models with a spectrum learning technique today. If you are still interested, say, in hearing about healthcare, that could be included as one of the optional topics, for the next few days. But just let me know or express your opinion on Piazza. Okay, so let's get started. So spectral learning on graphic models. It is a very active topic about 6 or 7 years ago. And now, of course, with the swiping interest in deep learning, many of these more kind of nuanced technology are not practiced as often. But I still feel it's a very nice idea that you can see, in maybe improving or in augmenting existing technique may also motivate new designs down the road. So let's see why that's the case. Just a recap, so far we've gone through many latent variable models, right? So here are a few examples. This is HMM, and the edges on top of that represents a long-range interaction or dependencies, so that you don't have to be first-order Markovian, but also higher-order Markovian. And this is a model used in sentence parsing. You give a sentence, you have a part of speech tagging, and then you need to come up with a latent tree to parse the sentence, for interpretation or for sentence generation. And this is a model which is very similar to the LDA topic model, where it's applied to social networks. It's called the mixed membership model. And you can see social actors can be projected into some latent space so that their clusters or dependencies can be visualized much better. So these are basically a wide range of latent verb models. And this is just a more explicit example about the probabilistic context-free grammar. And this is known as the latent variable probabilistic context-free grammar. And in this case, the PCFG is a classical NLP model where you need to have human labels of the internal structure, like this part. And then you train a probabilistic CFG models. Right? This latent variable model does not assume that this latent tree is given. You are only given the sentence and also the part of speech tagging. And then you are going to infer the latent structure. Therefore, it is, of course, way more difficult, but also it's less reliant on high quality labels from users. So how to learn such model, right? So I guess now at this point, you should be very well aware about a very common technique known as the EM algorithm. You are going to basically iterate between an estimation step and a learning step. In the estimation step, you are going to now come up with the imputation of the latent variables, and then you treat them as a fully observed model in the M phase and learn the estimation, and then you iterate. Right? And we should by now also know that there are a number of difficulties or shortcomings of this technique. One is that EM algorithm is very slow. It really requires a iterative algorithm which may or may not converge. And secondly, even if it is converging, the loss function contour of the latent verb models is always non-convex. Therefore, you may run into a local minimum. And the way to overcome a local minimum is to have a multiple random initialization, maybe 100 different initialization, and that further adds up to the slowness and makes the algorithm more expensive. So spectral learning algorithm is a very, very interesting and intriguing idea, which has nice theoretical properties. It is provably consistent. It is also offer good insight into the identifiability. So these are nice thing about the spectral learning algorithm. And practically, it is also free of local minima because there isn't latent variables involved. And it is therefore very, very fast because it's not a very, very expensive iterative algorithm. And also it is very flexible. It does not really need you to assume Gaussianity, discrete random variables, and so forth. It can be applied to all types of data with some tricks and ideas borrowed from kernel learning. In fact, there is another topic called the reproducing kernel Hilbert space technique, which we could also make them as an elective topic, which is not covered here, but I'm going to mention the ideas in terms of how they can further boost spectral learning. So these are all the advantages. It sounds like a very ideal technique, for learning all graphic models, but of course, we are going to see very, very shortly, there are also some difficulties in this technique. The difficulty are mostly conceptual because it is algebraically less straightforward, than a graphical model, standard graphical model technique where, all you need to know is to know a few distribution family, know the factorization rule, and then you assemble them. In spectral learning, it's more complicated. So here I listed a few representative papers. You can see that this whole thing started roughly a decade ago. And there are some major new developments in the following few years. And I haven't been tracing so closely in the immediate past few years about the new development, but my impression that it is not as active as before for obvious reason, because it is less straightforward. It's not so easy, to deploy and to develop. But still, there are very, very strong properties of this technique, which I encourage you to explore. All right, so let's see, why we have, a opportunity, to invent a new method, which is the spectral learning for latent variable models. So let's first maybe ask the question, why we even develop, in some cases at least, a latent variable model, say this HMM, okay? Why we develop a HMM? Well, you may say that I just want to know the latent states. I literally want to know that, say in our dishonest casino example, we want to know that how the dealer is playing a trick and what is his strategy and so forth. Right? So these are all nice goals. But at the end of the day, I want to basically challenge you. Yeah, why do you know all this? Is that just because of curiosity, or you want to just win your bet? Right? I guess most people, will say that. Well, I actually don't care about all these, latent facts. I want to win a bet. If you can help me to win a bet, I don't even want to know anything. You just, play it for me with my money, right? So that could be somebody's attitude. Therefore, if you see a partial sequence like this, being able to make prediction on this one and this one is the major goal. And the latent variable are basically one of the vehicles to lead to this point. So that's basically, a insight I want to bring forward. Because if that's the case, for our learning task, then we may think a little bit differently about how to design the problem, okay, especially in this dynamic system. Let's say predicting the future, given the past, is our major goal. All right, so if we focus on prediction, then we ask, do we still need the EM algorithm to learn the parameters? Well, yes and no, right? If your model is like a HMM, like this, you of course need to know the latent variable because that will give you the conditional probability of a P of a Y, T given, yt minus 1, and then, you know, xt given yt. Therefore, you can build on the sequence to predict the future. But in our Bayesian technique, in fact, in the past few lectures, when we talk about non-parametric Bayesian, remember the Chinese restaurant process and the Indian buffet process. What we do is to integrate out, right, those generative models that is generating, say, the seat configuration or the feature configuration. Our technique there was to really predict, say, z of n plus 1, which is the n plus 1's customer or a n plus 1's object, given the entire sequence of 1 to n, right? And then there is a predictive function that you can achieve, can obtain by integrating out, you know, those hidden distributions of the class label allocation. You directly make a prediction of the new label, right? So that idea actually can be used, in fact, in any latent space models. So in here, in graphic model, in HMM, we could imagine this part gets integrated out. So if that's the case, what's the consequence? Why didn't we do that? You know, in many of the you know, complex graphic models like HMM. Yeah. So here is why. Once we, you know, integrate out this, you know, you'll probably imagine, based on our CRP example, these all observed variables will start to be dependent of all each other, right? So that's basically, you know, something that you should be able to convince yourself. And at the end of the day, that leads to a model that is a clique. If every one of these random variable is dependent on any other random variable, then essentially the topology is a clique. That kind of beats the very purpose of our you know, graphical model design, because a clique really can be only described by, you know, a contingency table, you know, of all configurations. And then if you have many random variables, it will be very, very big, right? So that's not necessarily a very good idea. It is fine maybe if your goal is like doing simple clustering things like this, but for many other, you know, more complex tasks, using a clique to model the whole thing is not a good idea, because here you're only contingent on the count of the previous patrons. But in here, you may actually need to look at not just the count of every individual, of all the individual, but the actual, you know, behavior of every node. Then that modeling task will be very, very big, right? And you know, mathematically, why that's the case? Because integrating all the hidden variables really means a summation over this factored distribution. And because after the outer sum, the whole, you know, subject cannot be further, you know, factorized. Therefore, you get the clique. So now let's see. You know, obviously, a clique is very different from HMM. But what is exactly the differences? You know, if we're going to be using a more actionable algebraic description. Okay. Of course, the difference is that there is a graph and there is a clique that look different. But algebraically or computationally, what is the difference? Other than just the representation, either by a team, a group of small conditional probabilities, or a gigantic truth table probability. Maybe here is a way to look at it. So here I have a very simple graphical model of 3 observed random variables, all connected to one hidden random variable. Okay. And obviously the hidden random variable h has a cardinality. You can imagine that it has a number of states. Basically, the cardinality of h is, let's assume that the cardinality of x all belongs to, all equals to m. They have m states. Okay, and this one also has a number, right? It could equal to k. Okay, so now let me ask, what if k equals to 1? This is an algebraic statement that the cardinality or the number of states of the hidden random variable equals to 1. Does it actually have anything to do with the way we draw a graph? That's the question. Okay. Any guess from you guys about how the graph may look like if k equals to 1? Anyone want to shout out?
The nodes will be independent.
They will be independent. Can you try to make an explanation why that's the case? You're right. Actually, that's an excellent answer. But how did you get to that point?
Because that's what it said on the slides.
It's in the slides. Okay, perfect answer. Yeah, thank you. It's good that you read the slides first, and that's always a good thing that you prepped the the material. And the reason actually will be in the next slides. But you're right. You can imagine intuitively if basically h equals to 1, that means it doesn't matter what value h take. H x1 and 2 and 3 will just behave the same as if there is no influence from h, because it has only one value to take. Right? That actually gives you a kind of an intuitive guess that these three things will be independent of each other, because there is no hidden cause which can be used to impact the three random variables in any way different. They influence, but they will be influenced in the same way. Therefore, that influence can be neglected. Okay. In fact, algebraically, we can also prove that in a second. But let's ask, what if h has many states? Say h equals to k equals to m cubed. Right. Then actually, you probably could also convince yourself. In this case, you actually get this. It's a clique. Okay, so you can see these are two graphs. One is this one, and the other is this one. They are different graphs, but they correspond to just a different way of defining the cardinality of the hidden variable h. And the reason it's becoming a clique is because here my h could assume a value which correspond to every possible configurations of the three observed random variables. Therefore, all configurations of the three random variables is honored and assigned a different kind of latent state. Right. So that's why a clique is exactly correspond to that. You basically allow all dependencies to take place. Okay. All right. So the question is that what if my k is between 1 and m cubed? Right. So that's a little bit harder to answer. Whether it's going to becoming a between three independent nodes versus a clique. There are, of course, you can have two edges, but there are also a continuing of many stronger or weaker dependencies, right? So that's actually beyond what a graph can describe. And that basically leads to a alternative view, which is called the spectrum view of the answer. Okay. So before we go to the spectrum view, let's just mention briefly about some of the algebraic expressions we are going to use down the road, and which correspond to I mean, the linear algebraic rule will correspond to our probabilistic operations that we talked before. So one rule is called a sum rule, which corresponds to the marginalization of a joint distribution. So here is how we write down a joint, a conditional times a marginal, and then this one gets you to P of X and Y, and then we sum over Y, and then we get X. And linear algebraically, we use the following matrix algebra to express that, okay? This one is a table, this one is a table, and this one is a vector. And by doing this, matrix algebra, we get down to matrix times a vector leads to a vector, okay? So this is called a sum rule, okay? By the way, here we all assume that the random variables are continuous. We are discrete. For continuous ones, we're going to talk about later. There's a technique to cover that. The next one is called chain rule. Basically, this is how you get to the joint by multiplying conditionals. Okay, and the equivalent matrix algebraic operation is this. Okay, it's now becoming a matrix multiplied by not a vector but a diagonalized vector, a matrix. Okay, here because if you put y into a vector, it will get marginalized, summed out, and leads to a marginal over x. But if you put the y into the diagonal elements of a matrix, then you actually would not sum them out, just like this, and then you still get a matrix which describes the joint probability of two random variables. Okay, so sum rule and matrix rule. Okay, now let's see the linear algebraic view of a graphical models. Okay, so A and B each have m states, and therefore the joint can be described by a table. So in general, we cannot really say anything about this table, right? Because they can have arbitrary dependencies, and therefore all configurations is possible. But let's imagine this a graph where A and B are independent of each other, right? So if A and B are independent, then you can rewrite the joint into a product, basically P of AB equals to P of A times P of B. Therefore, a column in here, a row in here correspond to A equals to one of the value and then B taking all other values, right? And therefore, all other rows will pretty much be this part times another, P equals to another value, maybe A equals to M, for example. So in this case, the matrix actually has a very, very explicit property that their rank equals to 1, right? So this is the definition of a matrix rank, So there is now a direct correspondence between a matrix of the joint probability versus the graphical model of this pair of random variable. Rank 1 matrix correspond to a independent graphical model for the two random variables. Okay, and then if the two random variables are actually connected in arbitrary and all configurations are possible, then we still have a matrix which has a full rank. Therefore, it is of M. This is the highest rank, in this matrix because A and B each can take, just one value, M values. Right? So now let's see. If I give you a matrix but it has a rank between 1 and m. What graphic model you have? Okay, that's the interesting question. In fact, there isn't a explicit graphic model anymore, right? Because that's the only two ways two nodes can be connected. You kind of can imagine there's something in the middle which is weaker, but you cannot just have a graphical expression of that. So that's basically what's happening between for a k that is between 1 and m. Okay. So that means for a low rank joint probability of A and B, you need to introduce some arbitrary ingredients to augment the graphic model. In fact, that actually gives you an extra degree of expressivity. For example, here I can introduce a latent variable, okay, which can have a k number of states. It turns out that a rank k, table of the joint of A and B correspond to this graphic model, where the latent variable can explicitly capture the rank of that matrix. In fact, you can also prove to yourself that the joint probability matrix of A and B, their rank is going to be smaller or equal to k if the latent variable connected in this way has a rank k. Okay. So how that is proven? It's very, very easy. Basically, you can imagine the following matrix factorization. Okay, this is pretty generic. You can introduce a diagonal matrix expressing, the states of x, and then you can factorize A and B, conditioning on x in this way. And then if the rank of the x matrix is bounded by k, then because of this matrix factorization, we can conclude that the P of AB is also bounded by k. Okay. So what I'm trying to say is that the spectrum view of of the graphic model actually is having a very, very nice correspondence to the concept of hidden variables. And it captures the cardinality of the hidden variable, and therefore allow different degrees of dependencies between the observed random variables. So what I did here is that I set about a matrix with a lower rank than the full rank, and then they correspond to the hidden variable. But the other way you can go is that I would not care about the hidden random variable because it's going to cause me to a more complex learning algorithm like EM algorithm. I'm going to only worry about A and B directly. Okay. But I can really use a low rank P of AB for this pair of observed random variable, which effectively accommodates the presence of a hidden variable. So I'm going to go from here to here, right? Even though, to understand, the low rank K, I need to introduce a hidden variable. So these two concepts are equivalent. Okay, so this is the spectrum view of graphic models. And it is a very, very nice technique which enable us to use many of the tools in linear algebra to exploit the structure. You can see we already said about the concept of rank, and we also know what is an eigenvalue, and there are also various techniques such as SVD and tensor techniques to deal with linear algebra entities, which will make the learning procedure rather convenient and easier. Okay, so now let's look at a more interesting example. We have now multiple hidden variables, each of which has a k state, okay, and observation are m states. And now let's look at a bigger table, okay. let's imagine that this is our joint probability table, and on the row, the rows are indexed by the states of the first two random variable. The columns are indexed by the states of 3 and 4. Okay, and again, with the proof we had before, because the latent variables, has a rank k, we can show that this matrix also has a rank k, okay, even though the size of this matrix can be very big. In fact, it is actually, how big is this matrix? Anybody can answer me? I don't think this is on the slides. How big is this green matrix? Anybody? Yeah, 2m by 2m. Yes, I got two answers. One is 2m times 2m. The other is m squared times m squared. I believe the next one is right, m squared by m squared, because here the index is on the joint configurations of the two random variables. Therefore, you get 2m squared. Thank you. Great. So m squared and m squared is a very big matrix, but because of the latent variable rank, which is known, okay, then it becomes a low rank. Okay, and why it is known? Well, because it's by design. For example, I just want to have m hidden states. The dealer only has, say, 2 choices, right? So then that makes 2. And so how to prove that? Well, same thing. We can prove it by a matrix factorization. Let's just imagine a general kind of a matrix factorization. Suppose it is a m by n matrix, and then we can always factorize them, with a m by k and k by n. K can be arbitrarily chosen, right? So we have 1. And in fact, given this matrix, we can easily, do that, with, a factorization that corresponds to exactly this idea. Okay, you can just condition the first one on the latent state, and the next two also on the latent state, and the latent state, of course, has a k state. Therefore, we have now a expression of this bigger matrix with a combination of the expression using smaller matrix. This is actually, again, going back to our factorization, principle, right? We use a smaller conditional distribution to assemble a bigger one, and that's exactly what's happening here. But again, this particular factorization requires hidden variables to be introduced. Now, if you play with a linear algebra, often you know that every matrix does not have just one, factorization. In fact, there are arbitrarily many ways of factorizing a matrix. It is not unique. For example, given this one, you can always introduce a invertible transformer, a transformation in the middle, and then that gives you this and that, right? So that's another, factorization. The spectral learning algorithm has this magic that by choosing some appropriate S, it can lead you to a factorization of the M using matrices that only includes the observed random variables. Therefore, no hidden variable is needed. Okay, that's basically, a very interesting property that let's, take a deeper look. Okay. All right. So imagine that, again, we began with this full matrix. And there are a couple of, observed matrices of a subset of random variables, which are smaller, say 3 random variables. Let's look at these 2. Okay. And you can also express this tool, using further kind of factorization with even smaller matrix. And here are just two approaches, right? So the P of x1, 2, 3 can be factorized, can be pivoted basically by H2 and factorized into this matrix and that matrix. And likewise, you can use the hidden variable H2 to pivot x2, 3, and 4 and get the following, factorization. Okay. Now, let's just look at these two lines together. Those matrices that I underscored with a green bar, if you multiply them together, you get what? You get this, right? So x1 and 2 given h2 times p of h2 times x3 and 4 given h2 gives you the joint of x1, 2, 3, 4. Right. And the other three factors, which I underscored with a red bar, can actually lead you to a joint of x2 and 3 only, two random variables. Okay. So now if you multiply them together, this part and this part, on the right-hand side, you will have this times this. On the left-hand side, you have this and that. Therefore, you can prove to yourself that you will have a new factorization where P of x1, 2, 3, 4 can be expressed with a product of P of x1, 2, 3 and the P of x2 and 3 inverse and P of x2 and 3 and 4. So this is very magical because in here, this factorization contains no hidden random variables. Okay, all matrices are observed. Therefore, you can imagine in order to learn a model of the joint, you only need to collect statistics for this part and this part and this part. There is no need to estimate the hidden random variable h, unlike what we do in HMM. Okay. And of course, you have the nice reduction because now information are stored in the 3 random variable matrices rather than 4. Okay. Are you still with me? There is a caveat in this, as I said here, that even though these two matrices has this nice property of being a joint of 3 hidden random variables, or not observed random variables, but this one is a inverse, of a joint of 2 random variables. So inverse of a probabilistic table is getting you something that is they don't have to be even negative, non-negative. It's a matrix of numbers. There isn't a explicit probabilistic meaning for that matrix. Okay, but you can still obtain it and compute it. It's just that the interpretability part of this is not as explicit or straightforward as what a hidden variable would provide you. Okay, so this factorization is known as the observable factorization. Okay, so graphically you can see, this factorization correspond to, a pivoting operation on graphical models. We are going to introduce a pivot on H2, and that basically, allows, the full matrix to be, divided into a few pieces, each of which contains the only shared variable in these 3, will be the x2 that they actually, this pivot, pointed to. So for example, this first matrix contains x2. The last matrix also contains x2. And this one also contains x2. Okay, and that's why it is the right pivot. You can also use x3, that's also h3 to pivot, that's also fine, will give you the same thing. Okay. And you can also have an alternative expression, but like this, that's also equivalent. Therefore, it gives you the way of learning the same probabilistic matrix differently. And that gives you, and if you want to combine them, that gives you more flexibility of getting a better answer. Okay. All right. So what this slide shows you just a glimpse of the relationship to the original factorization, which is based on hidden random variables. Basically, the relationship is it's just a particular way of manipulating, the matrix, the factorization matrix. Once you make a particular choice of that, you basically are getting, the originally latent factorization into a observed factorization. So this part is not as interesting. We can just pass that. Okay. So to sum up, you can use a observed factorization now to break a big observation matrix into a product of small matrices, each of which only includes the observation random variable. And of course, in here you don't see much advantage. It's just reducing variable the size of the matrix from 4 to 3 and 2. But this trick can be applied recursively. For example, here we have a 5-variable sequence of observations. You can use the same observation factorization to divide them into a 3-variable matrix, a 2-variable matrix, and a 4-variable matrix. And obviously, this 4-variable matrix can undergo a subsequent factorization into 3, 2, and 3. Okay. So you can imagine that for any larger random variables, larger sequence of random variables, you can use this trick to recursively divide them, and eventually they can be expressed by a product of observation matrices of manageable size, like 2 or 3, or maybe a little bit bigger. Okay. And in training, what you do is to just collect sufficient statistics, from samples, okay, of the variable of interest in your building blocks, and then when you are doing the testing, you are going to introduce your tested configuration, and you look at this big table, and then you basically multiply appropriate matrices that is consistent with your observation sequences, and then get a number. Right. So you can see here the learning. Okay, this is the learning part. It's very different from a EM algorithm, which requires you to learn, latent parameters, such as the probability of HT given HT minus 1. So this is basically the latent parameters, right? Or the emission parameters, like X given the H for every T. Right? So to do that, you have to have an EM algorithm. But in here, this is like just the trivial maximum likelihood learning with all observed variables. You just collect counts, and then they will be used in this way to compute the probability of any future prediction sequences. Okay. And it is consistent because ML, you can easily prove that MLE estimator of a probability measure is going to be consistent once you have a large enough data set. Okay. Of course, it is not very statistically efficient. Okay, so let's see how we can apply that. So here is one possible applications. Remember our sentence parsing applications I mentioned earlier, right? In the past, we rely on a supervised technique where the user has to label both the language sequence and also the hidden trees of the parsing. But in a unsupervised parsing, we are given only, the sequence and also the part of speech tags, right? And your goal is to, estimate the hidden, parse tree given the sequence. How can we do that with a spectral approach? Well, we can see that, traditionally, you write down a latent variable model like this, right? And then you train it using an EM algorithm, and then you plug in, the observations, and then compute the observation. But in a spectral approach, it's dramatically different from that. What you do is to come up with the right matrix factorization. This is a 5 variable matrix, a 6 variable matrix. You divide them into a product of all these blocks, which can be directly estimated from the observation. So in the training, you just compute this, and in the testing, you query the probability, with any observation sequences. Okay, and that of course amounts to just very easily a sequence of tensor multiplications. Okay, no hidden variable is needed, and this model is still consistent. So, any questions so far? Is that too good to be true that we are now free of hidden variables and basically can bypass all the hidden variable design and directly learn arbitrary latent variable models just by counting matrices? Any kind of doubts or reservations about this technique that you see so far? Say, this is illustrated in this example already, right? So what's wrong with this equation? Or that they're good for us to go? Any questions at this point? Are you all with me? Okay, I would pose a few questions. First of all, given this whole sequence, coming up with this factorization actually requires some technique, some algebraic insight. I may not know the right way of describing or factorizing them, with this and this and that, especially when matrices are too many, where multiple factorizations are possible. Maybe there are some better ones and some poor ones. I don't know whether, I'm able to establish a factorization which has the equivalence to my original sequence. So there's an algebraic kind of knowledge needed. And the second thing that is even more problematic is that here we have an inversion. Whether this inversion exists or not actually is a question. We don't actually know. For example, if P of X and 2 and 3 is a rank deficient matrix, say rank 1, can we invert it? Not necessarily, right? The low rank deficiency may due to just the data is too poor, or just because there is a preferred kind of additional dependencies that I want to independence I want to capture, which make 2 and 3 not arbitrarily recombinable. Right? So these are just some practical issues. Okay. Let's first worry about the inversion issue, because this is going to be confronted no matter how you factorize the matrix, which is of course very skill dependent. Imagine you have that skill. When we can actually assume that this one inversions exist. For algebraically, it's very, very easy to establish, right? As I said, it has to be full rank. And what if my actual size of the matrix is greater than the rank? Okay. So this part is, for example, if my let's see, the matrix here has a lower rank, then what do we do? Well, that part is easy. If K is smaller than M, we can, use, a dimensionality reduction technique so that this higher rank matrix can multiply to a loading matrix or a dimensional reduction matrix to project them into a lower rank, lower dimensional space, so that they become, multiplicable, with a lower dimensional matrix. So this one has a rank K, and I can literally use this trick to make them able to work with a higher rank M matrix in here. Okay. And the U and the V matrix needs to be designed so that they have a good a matching rank with both the left matrices and also the right matrices. How to, of course, design V and M and U? That's a little bit tricky. In fact, it's almost like you bring back the latent variable problem. This matrix needs to be estimated, okay, if you want to estimate it. Or you could also just design it, just put in a M by K matrix the way you want. But again, the results may not be so good if somehow the rotation they caused on the original matrix confounded the factors or caused a loss of information. That's possible. But at least algebraically it's doable. What's more troublesome is that what if the K, the hidden states, we want a design where the hidden states has a higher cardinality than the observation. This seems to be a bit odd, but that's a design choice we could have made. Okay, let me give you an example about when that could happen. Okay, say, hey, this one has a high K. When this could happen, and if we want this to happen, how we can come up with, say, a matrix factorization which honors that kind of property. So imagine, say, this particular generative process. Okay, I'm going to have the following operation with probability 0.5 and 0.5. I'm going to generate two symbols, X and Y, which you will observe. Okay, but also I'm going to allow a character A to be printed n times in the observation, just based on maybe say a random choice of n. Okay, the choice of n, of course, is also a hidden state you don't know, therefore it could be anywhere from 1 to n. At the end of the day, you are seeing sequences like this. Okay, so in these two sequences, how many observations you have? Like, what is n? Yeah, the question is that I have a question. Does this method only apply to discrete? Yes, so far we discussed only discrete, and toward the end of the lecture, we're going to talk about how to work on continuous. Okay. But that's a good question. Okay, so anyone has an answer to my question? What's the m in the sequence you see? M equal to 1. Well, we already see X, Y, and A already in here. 3, yes. 3 is the right answer. Literally, it's here. You saw 3 characters, right? What is K? K equals to 2. Really? then how can you account for the number of A's appeared, in the observation? Right. So K is actually in here 2n. That's the answer. Because you need to not only remember what to produce for the symbol X and Y, but also to remember how many times A is produced. In a sense, you are going to remember, a whole sequence of n. For example, if you decided on n equals to 10, then you have to keep tracking on the number of A's. Am I going to see 10 A's already before I produce X and Y? Right. So therefore, there's a tracking number that is, of course, part of the hidden states. So in this case, this will be way bigger than the M. So that's a very nice practical property that sometimes my hidden variable model wants to have. In this case, you can see what it's essentially achieving is that it is no longer a hidden Markov model of first order. It is really capturing now longer term dependencies. I'm going to now look at the history and check how many A's I already have before I reach N and produce a X or Y. Right, so long-term dependencies. So long-term dependencies basically requires M or K to be greater than the M, than observations. Right. So how does the spectrum framework does that? Because it causes the matrix to be higher rank, therefore it is not invertible than the observations. So here is a technique. Okay, if we have a long-term sequences which causes the K to be greater than M, then we can use another technique where we are going to change the way this matrix is going to be defined. For example, recall our matrix factorization here. Once you're pivoting here, your matrix is always very, very straightforwardly described by this kind of a short range coverage of the next 1 or 2 random variables in the whole domain. If you have a longer range features like I do have in here, you can now, instead of writing down a table of say 3 matrices, 3 random variables of m dimension, you can actually introduce a arbitrary feature vector, which allows you to describe anything you want to describe for the sequence of this length. Okay, and this feature vector is up to design. Okay, you can basically write the number of A's I see, or for the past 1 to K positions, is that an A or not? Something like this. So it's an arbitrary feature vector. And likewise, you can have a right feature vector, for this with respect to this pivot. And then this matrix originally is the truth table of the configuration of XY only, now becomes an outer product of the 2 delta vector. It is originally in here, it's the delta vector describing just the configurations of X and 1 and 3, right? I'm going to now replace them with the left and the right feature matrices, or feature vectors. So this is a trick allowing you to really, incorporate a far more number of, features than M. So here, remember, it could be only M because the delta of X2 can only take this many, configurations. But this phi of L and R can take way more features, number of features. Okay. Therefore, what you have is this matrix instead, which now has a very big K cardinality. And then they can again get to match to the left and the right matrices. Okay. Okay, so that's basically just a rough idea about the feature trick, which gives you appropriate ranked observation matrices. The important thing that they are all observed. You can still just bring in the counts into this feature function or the original probabilistic table, and then without resorting to any hidden random variables. Okay. So Anker, who is my former student, he actually worked quite in depth on this technique, and you can see from this graph, that technique can be applied to higher order Markovian model, factorial Markovian model, tree models, and so forth. And he actually did a lot of experiments, on the quality and the efficiency of learning this type of graphical models, spectral graphic models. And you can see some comparisons in here. First of all, the speed advantage, right? You can see that, a EM algorithm or a online EM algorithm, which is, it's an EM, but, every time it is taking the latest window of the data and do the online update rather than the batch update, you can see that the efficiency, runtime of a EM algorithm is really growing exponentially. So this is an exponential scale with the number of training examples, right? And if you see the spectral algorithm, it is going, not quite exponentially, or with a much, much smaller number in here. So it's more efficient, orders of magnitude more efficient. In terms of the quality, say the error on prediction, here is a comparison. At the beginning, with a very, very small number of training examples, you can imagine that EM, because of the complexity of the EM and the hidden states and all that, it usually requires more examples to get a higher training quality. Otherwise, they will be, stuck into some very bad local minima. Therefore, at a small sample size, the spectral algorithm does better, not only faster, but also better. With more and more examples, the EM algorithm picked up and start to do sometimes even better than Spectrum or as good as Spectrum. Okay, that's basically when EM see more examples and gets a greater statistical efficiency. But interestingly, if you keep growing the example to very big, the EM algorithm does poorly again. Why? Because the size of the complexity of the learning task actually grow with the number of examples in latent space models. Because when you have more and more examples, you are going to estimate more and more hidden random variables for each of the observation. And you are having more chance to commit mistake because your problem becomes larger and larger. So basically, that part outweighs the statistical strength of the data to the estimator. Therefore, it becomes poor again. But for Spectrum, there isn't such a property, such a phenomenon. It will keep going down once you have more and more data because the complexity of the problem didn't increase. You don't really have any growth on hidden variables to be estimated. You only have more sufficient statistics in your observation matrices. So that's the nice property of a Spectrum technique. And there are some empirical comparison done by Shea Cohen on the supervised parsing versus unsupervised parsing. In fact, the comparison was done by Anker. The reference point, the supervised parsing, was by Shea Cohen, which is based on a probabilistic context-free grammar. And this latent one, as I mentioned before, does not require labeling of the parse tree. Therefore, it is easier to train. And you can see that the performance, even though it requires much weaker and easier data, the performance are comparable. Okay. Okay. And but on the other hand, the speed is way more kind of efficient. You can see it's usually an order, if not 2 orders of magnitude differences. Thank you. All right. Now we have 10 minutes left. We can deal with a few other additional technical tricks. So when asked, actually I have a question here. What does it mean training examples equal to 0.1? Is the x-axis log scale? Yes, I believe. Good point. Yeah, I believe it is log scale. Okay. All right. Thanks. All right. So one of the question I just heard was about how about continuous random variable? Yes. So all what I said just now, which is built on having a matrix of x and 1 and x2 p. Of course, it's a making assumptions on discreteness, right? But we still, unfortunately, it's not covered in this course. But there is a family of technique known as the reproduction kernel Hilbert space embedding. Or Hilbert space embedding using reproducing kernels, where you can really pursue a transformation of entities like a sample from a discrete or a continuous distribution, or even a distribution itself, into another Hilbert kernel space, a Hilbert space, which allow a vector kind of expression. For example, if you represent a distribution in a Hilbert space, they can be expressed by a mean parameter, a mean vector. Okay, and if you have a example, okay, in the Hilbert space, they will be another transformation vector, which allows the nonlinear transformation of the original vector into here. In fact, it could also be an infinite dimensional matrix where this cardinality of phi could be infinite. But using the kernel trick, we can always deal with just the dot product of the feature vector. Therefore, you don't have to even deal with the infinite feature vector, even if you have a expression of the feature vector in a infinite dimensional space. So these are the techniques it's well established in the Hilbert space embedding technique, which is not going to be discussed in today's lecture at least. If you're interested, we could use also one of the elective lecture to discuss that. So now let's see how our matrix spectrum graphic model technique connects to the Hilbert space embedding. Remember, originally to obtain a joint probability table, we use the following operation. The joint probability table is literally just an expectation of the incident vector. So these delta vectors are picking observations, right? If observation equals to some value, then the delta function corresponding to that value will be equal to 1, therefore picked up. Otherwise, it is set to 0. Right? So this is just a algebraic expression of picking observation values into the table. And we also just mentioned that we could replace each of these, the delta vector is literally just a vector of 0, 0, 0, 0, 0, 1, and so forth. 1 is the case dimension. That means that, so basically delta, k actually correspond to what? Correspond to x equals to k. Right, picking just that number. But this vector can be more kind of general and replaced by a feature vector. okay? And therefore, the feature vector could be any numbers in here. And in the past, we say it can be used to capture long-term dependencies happening before x2 or happening after x3, right? And then, the operator can be now alternatively, defined as a covariance operator. You are literally just compute the covariance of these two outer product of these two feature matrix, feature vectors. Now you can imagine that instead of just designing this feature vector, which captures the long-term dependencies of hidden states, over a higher order Markovian fashion. You can also imagine that this feature vector, this phi vector, is just an embedding of the original observations into that Hilbert space. And also, do you actually need to know the embedding itself? Well, since you are working with only the covariance operator, you could define just a kernel directly, okay, which could be a RBF or any other kernels. Okay. In that case, you are not going to be working any longer with the original observation random variable directly. You're going to really work with a covariance, a kernel matrix centered around these two. It could be you could imagine that it is just a some kind of a distance between x2 and x3, computed using some functions, right? So in that case, obviously you don't have to assume that x1 and x2 and 3 are discrete anymore. They can be continuous. They can be anything, right? And therefore, you have this seamless transformation from a discrete case to a continuous case using, all these covariance operators. Okay. So did I answer your question about the continuous versus discrete? Cool. Okay, so time is up. So let's get a summary. So I give you a very, very brief precursor, introduction of the spectrum graphic model technique. Right? You can see a side-by-side comparison. So in here, you really, are, working on, again, a MLE estimator, which is statistically efficient. Every example is kind of contributing to the estimation of the model parameters. But you have a number of technical problems, like theoretic guarantees, local minima, speed, and so forth. Another good thing that it is kind of easy to define, to derive. It's straightforward. The spectrum technique almost is a exact complement of that. It is not trying to find a MLE for those hidden states, okay, and also for the generative processes. It is directly, about finding out the joint configuration of the observations. Okay, therefore, it does not have any local minima. Okay, it is consistent. It is very, very fast. But again, it is very challenging to derive, for new models how to factorize. If I give you an arbitrary tree, if I give you, say, a LDA model or some other network model, finding the correct and the efficient matrix factorization is highly demanding, and you need to have the good insight and some linear algebraic skill, to find the right factorization. And then, of course, there are technical issues, such as, what if your matrices are yield conditioned, have negative numbers? Such thing doesn't exist, in the EM algorithm, but it can exist in spectrum algorithm. And therefore, we luckily have a good additional technique such as feature design and the kernel embedding technique, to accommodate that. These actually are the technique that does not play very well with the EM algorithm. It is very difficult to incorporate long-range features and also to deal with continuous random variables. So overall, this is a very powerful technique when it was invented about a decade ago, and for the next half decade, it was very actively practiced. There are spectrum versions of all almost well-known graphic models, including HMM, tree, topic model, mixed membership model for networks, and many others. And the trend suddenly gets a little bit slowed down with the birth of the deep neural network. I'm not convinced that this technique won't be useful for doing deep neural network. But on the other hand, doing spectrum mechanism, graphic model learning and inference requires some patience in developing the technique, such as finding the right matrix factorization of that. But deep neural network now has a TensorFlow and other auto-differentiator tools. Therefore, people can freely draw any architecture and then throw into a highly composable and highly automated inference engine to take care of the rest. And also, people worry less about those interpretability issues inside network. Therefore, I think the spectrum technique, unfortunately, become either neglected or receive less attention. So that's basically where we are right now in this technique. But it will be very interesting to see, whether bring in spectrum technique, just like what people did with Gaussian process on deep neural network, which results in some very nice performance improvement. Here, I'm also curious to see whether there are additional opportunities for combining these techniques. So with that, I'm going to finish today. Again, today's lecture opened a few new topics, such as kernel graphic models and reproducing kernel Hilbert space embedding and others, which used to be in the graphic model lecture. You could actually go watch the older lecture videos to get a sense about what those are. The slides were also available from the class website. But if you strongly feel we want to do a lecture, we can also do that. We can also do the machine learning for health. In fact, almost a half of you also voted for that. You are just 3 votes short of this spectrum graphic model lecture. So that means it's also an interesting topic. So that's basically what we're going to do for next week. We have 2 open slots for elected topics. Let's reconfirm your interest on the poll. On Piazza, and then we're going to conclude this semester. The TAs may make I don't know if they done or not. We did some adjustment of the final project presentation and the schedule, and well, I'm not sure if it's not posted yet. We're going to post the guidelines for that. In sum, you're going to get more time, and you're going to we're not going to have of course, a workshop symposium to, really go physically presenting the posters, but we will have some alternatives to make that happen. Okay, thank you very much. See you on Wednesday. Any questions, by the way? Okay, no more questions. Great. So let's close the lecture and see you on Wednesday.